All right. Last class of the week. So, what we'll do today is we'll start off by answering any questions about the homework that you might have from our chapter 13 stuff here. So in chapter 13 we learned about temperature, the different temperature scales, learned about absolute zero, learned about thermal expansion of liquids and solids, and we learned about the ideal gas law, so that we can compare things like temperature to things like volume to things like pressure and number of molecules or particles or whatever. And then the last thing we learned was about the kinetic theory of atomic molecular gases and how speed is related to temperature. Kinetic energy and temperature are essentially measures of the same thing. Gave you some homework problems on those things. So who's got a question about one of those problems?
For this question, physicists make a coffee, a cup of instant coffee, as well to show the level drops.
So he does what?
He makes a cup of coffee.
A cup of coffee. Okay. That's in 13.3? 13.2? Okay, let's take a look. Okay, so in this one, he makes a cup of coffee and notices that as it cools, the level of the coffee drops. So he's got this cup, and when it's hot, it's at this level, and then later on, when it's cool, it's at a lower level. So there's a change in volume, right? There's volume initial and volume final. And there's temperature initial and there's temperature final. We've got two things that have changed so far. And what we're going to do is they say that show this decrease cannot be due to just thermal contraction. So what they're saying is that this thing didn't get less volume just because it got cooler. Okay, that's one thing that could have happened. The volume can go down, will go down as the temperature goes down, but it won't go down this much. So it dropped 3 millimeters in this glass cup. So you have a 7 centimeter diameter cup. So it's 7 centimeters here. It drops how much? 3 millimeters? 3 millimeters. Drops 3 millimeters. That's the drop here. And 350 cubic centimeters of coffee. So this thing has a total volume. The volume initially is 350 cubic centimeters, right? So you can do this one of two ways. You're going to need to do some conversions. You can either convert everything to meters cubed, or you can convert everything to centimeters cubed, or whatever. I would recommend you convert to something different. Since we have centimeters in two things, we might as well just use centimeters cubed for our measurements. So we're going to convert everything to centimeters, which means this is 0.3 centimeters, right? And you convert them. You just have everything has to be measured in the same units. And what we're going to do is we're going to have a before and an after. We're going to have we're going to use the expansion equation. The expansion equation says that delta V equals V initial, and then we use the bulk expansion coefficient, whatever So volume expansion coefficient. I don't remember what they called it, but it's up here somewhere. Right here, we have the coefficient of volume expansion right here for water. Coffee is mostly water. So we'll use water, which is 210 times 10 to the minus 6. 210 times 10 to the minus 6 is our beta per degree Celsius, right? And also we need to know what the temperature change was, or at least something about it.
Minus
15 degrees Celsius?
50.
50? Okay, so delta T was minus 50. In other words, we have a temperature, this temperature final is the initial temperature minus 50, right? So that gives us something to work with. So what we need to do is we need to use our equation, which is delta V times V times beta times delta T. The initial beta, let's check that equation right here. Delta V equals beta V delta T, where V is the initial. So V delta, that's what it is. So we need to check to see if the change in volume is this change in volume. What is this change in volume? This change in volume here that we got was equal to 0.7 centimeters by half, so it's 3.5 centimeters squared times pi, that's the area, pi r squared times 0.3 centimeters depth. Right? So that's our change in volume. That's the thing that goes in right here. Later, we are going to compare to this one actually. But what we want to do is we want to calculate this using the numbers we have here. Calculate the change in volume that you would get from the initial volume times the beta times this change in temperature. And see if you get this volume. See if we get this one. This one ends up being 3.5 centimeters squared is about 10. Times this makes it about 30. Times 0.3 makes 30 times 0.3 is about 9. So this is about 10 cubic centimeters of volume change. That's how much volume change we had when we lost 3 millimeters, 0.3 millimeters, no, 3 millimeters of liquid. We had about 10 cubic centimeters of volume change. Let's see if this turns out the same. If this ends up being about 10 centimeters cubed, then it's all because it got colder. If it's not the same, if it's less, then something else was causing this to drop too. And we know something else causes it to drop because it evaporates, right? So what they're saying is that most of this is due to evaporation. But we need to check to see. So what's our initial volume? Well, our initial volume is 350 centimeters cubed. So that's our initial volume. Our beta is 210 times 10 to the minus 6. 210 times 10 to the minus 6. And then our change in temperature is 50, right? So 350 times 50, that's about 15,000-ish, you know. It's about 15,000, it's about 17,000 actually. So it's about 17,000, which is almost 20,000. And then you're multiplying it by this 200 million, essentially 200 millionths. So this is times 10 to the minus 6. So it's essentially going to multiply this by 200, and then we're going to take off 6 decimals. If we do the math, let's do it properly so that we get a good number. So we get 350 times 0.00020 times 50. Okay. I get 3.675 centimeters cubed. So that's definitely smaller than 10 centimeters cubed, right? So just because it got colder, we lost this much volume. The volume went down by 3.675 centimeters cubed. That's the amount that it contracts. But we lost another almost, 6 point something centimeters, or about 6 centimeters cubed of volume. And that amount of loss in the coffee cup was evaporated. That was just due to evaporation. So we find out that most of the volume in the coffee cup is lost due to evaporation, not due to cooling. The interesting thing is that as something evaporates, what happens to it? We learned that with the dry ice. What happened to the dry ice as the liquid carbon dioxide, as it evaporated? What happened when we opened up the container?
Soft cooling.
Yeah, evaporation actually causes something to cool more quickly. So probably we didn't even lose this much because, well, probably we lost even more. But anyway. So they kind of play off of each other, right? They encourage each other. I wonder if I've any dry ice. Probably all gone now. Yeah. Liquid nitrogen will have it for months. That makes sense how that all worked out?
I just didn't know. I understand how I need to do everything with this, but I didn't know what to use for that beta.
Oh, okay.
Because,
Didn't have a beta for coffee?
yeah.
It's mostly
I was
wrong.
Google on internet was a beta for coffee, but I didn't find anything. So.
Yeah, coffee is mostly water, so we just use water for the beta.
Next time, call me, let us update.
Call him up, he'll make you a cup of coffee. All right. Any other questions that you want to work on? The Zoom height.
Yeah, the helium filled balloons.
What's that?
Yeah, large helium filled balloons are used to lift scientific equipment in high altitude.
Which section is this in?
I don't know. I call it
It's 13.3.
there it is.
Large helium-filled balloons are used to lift scientific equipment to high altitudes. What is the pressure inside such a balloon? Okay. So again, this is a situation where we have a beginning and an end, and we need to compare the two. And that's how it is with most of these problems in these next chapters, in this chapter and the next one. Where you have one situation and then you change that situation by heating it up, or changing its pressure, or changing its volume. And you use the ideal gas law, which is the ideal gas law is P times V, pressure times volume, equals number of atoms in times K times T, or PV equals little number of moles, or T. Can be either one of those, depending on the problem. If they give you, well, anyway, there's different reasons why I would use one or the other over the other. But let's see which one we want to use here and what we want to do here. Large helium-filled balloons. So we have the pressure. We're going to try to find out the pressure. So the pressure is the thing that we are not going to know. We want to know pressure on the right. Pressure equals question mark. We might know it at one point, but we won't know it at another point. If it starts at sea level with a temperature of 10 degrees and rises to an altitude where its volume is 20 times the original volume and temperature, what is the gauge pressure? So, starts out at sea level at the temperature. So it's starting out at sea level. So sea level is pressure. We'll call that sea level pressure 0.
15.
What's that?
Sea level pressure is 15.
Sea level pressure is, if you're measuring absolute pressure, is 10 to the 5th Pascal. But they want to know gauge pressure. Remember, there's absolute pressure, which is the actual measurement of the pressure relative to zero pressure. But gauge pressure is relative to the pressure essentially outside. So if we start at sea level, we can go ahead and call that pressure zero if we want to, because we're just measuring the difference in pressure between that pressure and the pressure at the top. So we'll call that the original pressure. The next thing is to write down the original temperature. Temperature is 10 Celsius. And the volume, let's see, the original volume is just V, but the final volume is 20 times V. So in other words, this thing's going to get bigger volume, right? The final temperature is going to be negative 50 Celsius, right? The final pressure is something we need to know. Now, like I said before, there are two ways that you can do this. You can either solve these equations for all the things that you know, all the things that are constant, and then have on the left side all the things that are not constant, or you can do ratios. We'll do it both ways to show you how it's done. So all the things that stay the same, all the things that are constant, what does stay the same? Well, the volume doesn't stay the same, it changes. Temperature doesn't stay the same, it changes. Pressure doesn't stay the same, it changes. What does stay the same? The N and the K. Those are the two things that stay the same. So I would keep those on one side and put everything else over here, dV over T. Right? And then, once I've done that, then I can say P initial, volume initial, temperature initial equals this constant, so that also has to equal P final, volume final, over T final. And then I have an equation I can solve. So that's one way to do it, this problem.
Now, where do you get the P?
What?
The NK, isn't that like how much gas is inside the balloon?
Right, but that doesn't change, right? Since that doesn't change, since this thing doesn't change, if I divide by T, then this PV divided by T, the pressure times volume divided by the temperature, will always be the same number. It will always equal N times K. So if I do it at the beginning and I do it at the end, it's going to be the same number. It's going to be N times K. That's why I can make this state equation. The other way to do that is to say, if I do this equation twice, once at the beginning, pressure initial, volume initial equals number initial K times T initial, and then I divide it by the same thing done at the end, it's true at the end, it's just as true at the end as it is at the beginning. So I can just divide it. And this makes a new equation. If I erase that and put the equation right there, the ends cancel out because they're the same number beginning and end. The K is always the same number. And you essentially get the same equation. It's just rearranged in a different way. Either way, you're going to build this equation and you're going to solve it for the thing that you don't know. And the thing that we don't know in this case is the final pressure. Right? So if you solve for the final pressure, we multiply both sides by the temperature, final, pressure initial, volume initial, or temperature initial, We multiply both sides by the temperature final, we divide both sides by the volume final, and that equals your final pressure. Either way you want to set it up works. Now there is one problem with this, and that is if you do it this way, if you do this, you can't have your P initial being 0 because then that nullifies this whole side. So we just call this initial pressure P. We just call it P initial equals P. And P final will be some multiple of that. or you can actually plug in the atmospheric pressure at sea level, which is 10 to the 5th Pascal. You get a number out. Either way will work for the answer. If you want to put it in the, your final pressure is some multiple of the initial pressure, or if you want to put it in as a number, I don't care what the answer comes out as long as it's correct.
Kind of a contradictory statement there, sir. You don't care what it comes out as, just as long as it's
I don't
right.
care if it comes, if you write it as a number or as an expression of a factor. It's more to the point.
So if you put in the past, how do you get the gauge pressure? So you almost need to solve this for pascals and then take pascals and turn over to PSI.
What? No, just expressed in Pascal.
So you should use pascals at sea level.
Sure. Or just call sea level P. P0.
What we are using for P initial here?
I'm sorry?
What we are using for P initial here?
V initial also can be just V, because they tell us that V final is 20 times V, so that you'll get V over 20 times V, because V's will cancel. And your temperatures, remember, should be in Kelvin. In this equation, we use Kelvin temperatures. So don't put in 10 and negative 50. Put in 263, which is, 270, 283.
So you have to change it to Kelvin.
Those do need to be changed to Kelvin in these equations. Otherwise, you're going to get a negative number for the pressure, which wouldn't make any sense. Okay, anybody have any more questions? We ready to move on? Next chapter?
Really? You're going to sit over there and not ask me another question? Yeah, I'm looking at you.
Pot calling the kettle black, man. This class is out of control. I will be checking my email over the weekend. So if you have questions, if you're getting sick eating turkey or whatever it is you're doing, you want to do physics, you're welcome to email me.
I need to submit this homework next week.
What's that?
I need to submit this homework next week.
Absolutely.
The third one.
Which one is that?
I can show you.
Oh. Okay.
Shut up.
Milos can show everybody.
Yeah, go up on the board up there, Milos, and show me.
And you kept this conscious in your book. I was changing numbers. This is good question.
Like most of the questions are the PV equals PV, right?
Or something like that.
Yeah.
Yeah.
Where you got a big P or a little V equals a big P.
Yeah, it depends on what's changing. Right.
Yeah.
They're all variations on that. Yes?
When you mentioned that when stuff expands and it has a hole in the center, it expands away from the center, like from screws
Yeah.
and things like that. I was reading a book about Civil War era cannon, and they kept screwing up the castings, and it kept blowing up, and they couldn't figure out why it kept blowing up, and it turned out because they were casting it with a plug in there, like precasting the barrel, and that was the problem. It was causing it to cool that shrunk away from that.
Mm-hmm.
Got weaker.
Yeah, cannons are difficult. They pretty much have to be turned on a lathe in one piece.
And that was.
Yeah, you can't make them in multiple pieces.
So you can turn it on the lathe and you can fan the barrel.
Yeah, you can do that too, but those are certainly not as effective.
Yes.
The easiest way to make a cannon is to turn it on a huge lathe and want to cast it and turn it, cast it out of one material and turn it on a lathe.
We had to help us haul his cannon for Civil War shoots.
I had a friend that made his own cannon, his own Civil War cannon,
Nice.
and he used to fire it out in the desert all the time. This guy was the funniest guy. Born and raised in Los Angeles, California. When he was a kid, he discovered early on that he just didn't belong in Los Angeles because he was just a little too wild. Like he went up to on the hills above Los Angeles where now the Hollywood sign is. It wasn't there then when he was a kid. He's an older guy. But he went up on that Hollywood sign hill and he took with him his ramjet engine that he had built and designed himself because he wanted to test it somewhere where it would be safe. He lit this thing off and it just took off and he never saw it again. It just went flying. You know, it's a chunk of steel, about 10 pounds of steel, flying over Los Angeles. And he's like, oh crap. Oh. So then he married a girl from the Mountain West, moved out into the mountains of Utah, and he was a paleontologist digging up dinosaur bones out there in the high desert between Utah and Colorado. And while he was out there, he decided he wanted to live like the ancient Americans.
This is the guy you mentioned.
That's right. He makes his own bows out of by layering wood and fish scales and sinew and letting them age and baking them over fires. And he makes his own arrows and he makes his own arrowheads out of flint, not obsidian, but flint. So they're like hard as steel. And does all his hunting that way, except when he hunts with an atlatl and a spear. He's one of the only people in the United States who has made several, not just one, but several full-size teepees from scratch out of hide. No canvas. He's made them out of hand-tanned hides that he killed himself, and he stretched himself and everything. There's 2 of them in a museum up there that he built out of elk hides. He has some out of buffalo hides. He's just an incredible guy. What's that?
Valuable knowledge of post-apocalyptic situation.
Yep. Turned his own cannons, built his own. He held at one point the world record for the longest shot made with a Sharps 30 caliber rifle from the Revolutionary era. It's like a 1,800 yard shot, hitting a person moving on a horse. It's a shot that was a legendary shot by an old marshal who was chasing down some fugitive in the early West era and could only get that close to this guy. So he just set himself up on the top of the mountain and picked this guy off from a half a mile away. Well, actually, it's about a mile.
Were those smooth bores or were those rifles?
I don't remember.
Hey, they take kilometers a second.
I think they were
hours.
rifle.
You take it and divide it by 3,600, right?
To do what?
To take kilometers a second and get it 15 kilometers an hour. Divide by 3,600.
Kilometers per second into kilometers per hour. That'd be multiplying by 3,600, wouldn't it? Because you're going to have more kilometers in an hour than you would in a second. So you'd multiply. It's going to be a bigger number. 1 kilometer per second is 3,600 kilometers per hour. Which is moving. It's 3.6 million meters per hour. Any other questions, or should we? Let's move on. If you have any other questions, we'll come back to them. You guys ready to move on a bit and learn some new stuff?
Scott, are you ready?
Sure. Milos is going to come in to my house tomorrow and show me how to do everything I know right now, right? Milos?
If you want to be able to write closer to the presentation for Congress.
What did you say?
He's got to make He's got to make a poster presentation so he can get money for doing his research. What conference are you going to?
For good science, we have in St. Louis every year.
Yeah, you got to do presentations or you don't get any money for your research, man.
2 years ago, I won some prize, like best presenting poster.
Oh, nice.
Now I get $200.
Oh, sweet. Gotta love that.
It's pretty nice.
I'll tell you where the money is. That's grant writing.
Grant writing can bring in a lot of money. All the computers in this room are paid for by a grant. And that 3D printer. All right, so let's talk about thermodynamics. Heat and heat transfer. Do we really want to talk about heat transfer? Yeah, I guess so. Okay, so what we're going to talk about in these next 2 chapters, which are pretty much should be 1 chapter, in my opinion, we're going to talk about the concept of heat, which is different than the concept of temperature. Temperature is a measure of the internal movement of particles. Temperature measures how fast things are moving inside of a liquid, a solid, or a gas. Heat is the amount of energy that is required to get things moving, or to slow them, the amount of energy you got to take out. The amount of energy you put into something to change its temperature, or the amount of energy you take out of something to change its temperature, is the heat. So heat is a type of energy. It's measured with, the units of measurement for heat are the same as all other energies. We use joules for that, or we can use calories like we've used before. But heat is the actual amount of energy that causes the temperature to change, or causes ice to melt. So it is different than the temperature itself. So here is an example of an experiment done. This was actually done by Joule, the scientist whom the energy unit is named after. He had these paddles in this bucket of water and this contraption here that allowed him to, he would wind this up slowly and then sit and let it, come to equilibrium. And he'd have these masses. When he wound it up, these masses would come to the top of the height here. So they would be up at these top dotted lines. And then he put a thermometer in this tank of fluid where all these paddles were connected to this wind-up toy. And so he knew how much energy was going to be released when he released the handle. When he released the handle, these masses were going to fall from this height to this height, which would be a change in potential energy. that falling of the mass would cause the turning of the wheel, which would cause the movement of the water. And his thought was that if I move the water, it should increase the temperature, because movement of molecules is equivalent to temperature, right? And he was able to show that as he dropped these masses from here to here, if he had a well-insulated system, he actually was able to show that the energy that was lost as you went from a high potential to a low potential with these two masses was the amount of energy that was gained in the water, and he measured that by measuring the temperature. So very different kinds of energy. We've got potential energy gravitationally, turning into kinetic energy with the paddles, turning into thermal energy in the thermometer. So how is it connected? This is part of the work that he did, is connecting these by using an equation. He was able to put together an equation, and this is what it looks like. The amount of heat, which we use Q for heat, capital Q, the amount of heat necessary to change something's temperature is equal to the mass of the something that you change times the change in temperature times this constant again. Now, of course, there's always a constant involved, right? The constant is what makes this an equation and not just a relationship. The constant in this case is what we call the specific heat of the material, because every material heats differently. I might put 100 joules of heat into water and only get a small change in temperature. If it's a big mass of water, 100 joules of heat is not going to change its temperature very much. If it's a small amount of water, 100 joules will tend to change it more. But, so mass is definitely a key, but the other thing is if it's water or something else. 100 joules of energy might change water by a temperature of only 1 degree. But if I put that same 100 joules into the same volume or the same mass of alcohol, it will change its temperature more. Alcohol requires less energy to heat up. Okay? Other materials require more energy to heat up. Water is one of the hardest things to heat up. It takes a lot of energy to heat up water. In other words, water will absorb energy without changing its temperature very much. It will absorb a lot. So what does this C, with this specific heat, for different materials? Well, here's a nice little chart. They give us two specific heats for each material, one in joules per kilogram degrees Celsius. So if you want to know how many joules of energy it takes to change something's temperature, you use this one. If you want to use kilocalories, which are food calories, so this is for food calories, then you use this one. So for aluminum, it takes 900 joules per kilogram of aluminum to change it 1 degree Celsius. So if you want to change aluminum 1 degree Celsius, you need 900 joules of energy, and it will change 1 kilogram of aluminum 1 degree Celsius. However, if you want to change water 1 degree Celsius, it takes 4,186 joules. More than 4 times as much energy to heat water than it does to heat aluminum. Aluminum heats up very quickly, very easily. Water, not so much. And you notice that. Put an aluminum pan on your stove and turn it on. Go back 10 seconds later and touch the pan. Ouch. Hot. Even if you don't turn the oven on very high or the stove on very high. Put water in that pan. Then put it on the stove, cold water, and then 10 seconds later come back and touch it. You can lift it off the stove. Right?
What's happening with aluminum foils that we have? Because when we put something in oven, we cover it with aluminum foil.
So the reason you cover it with aluminum foil is a different thing. You cover it with aluminum foil to keep in the moisture and to reflect the heat back in. You're not using it as a heat, you're using it as a vapor barrier and a reflective surface, not as a heat surface.
But still, heaters are giving some energy.
The heat will still go through the aluminum very easily, which is good because you want the heat to go in there. So, but as you notice that aluminum foil has one side that's shiny and one that's not. So you put the shiny side in towards the food, and that keeps the heat inside. So it reflects back inside the food. So aluminum foil is used for a completely different purpose than an aluminum pan. Right? But you want a pan that heats up easily, because you don't want to lose all your heat in the pan. You want the heat to go into the food. So you want a pan that heats up easily. Even better than an aluminum pan is a copper pan. It only takes 387 joules to heat up copper. But copper is expensive, so not many people have copper pans. All right? If you go into some rich person's kitchen, they'll have copper pans if they enjoy cooking, because they can afford to pay $100 for one little tiny pot, right? Or $400 for a bigger pot. But I can't afford that, so I have aluminum.
Well, it's just for pot and lead.
Yeah, lead's not so good though because it melts at a very low temperature. Also, cooking in lead's not so good for your health of your children. But another one that's quite good is iron. So cast iron is almost as good as copper. But people don't like cast iron because it's heavy and you have to take care of it, because it rusts. So they make a compromise. They use stainless steel, which is not terrible. Let's see if they have stainless steel in here. Stainless steel is not as good as aluminum in some ways. Depends on the stainless steel. If you use carbon steel, it's almost as good as cast iron. So they use carbon steel a lot because it doesn't require as much work as cast iron does to keep it in good shape. Or they use a combination. Like I have stainless steel pans that have a bottom made of aluminum. So it's kind of a compromise. Anyway. So, I want you guys to do this problem right here, except instead of using an aluminum pan, I want you to use a steel pan. And instead of heating water, I want you to heat alcohol and do this problem. I'll be ready.
Yeah, I got all chapter 12 questions done. I need to do solve them for studying for practice.
That's what you should ask.
Huh?
That's what you should ask. That question.
Okay. Sorry for the interruption, but so temperature difference in this particular problem is 60 degrees. You go from 20 to 80, right? And that's part of this equation. Q equals mc delta T. We need to know delta T. But we're going to use this equation twice, once for the pan and once for the liquid, right? So the Q for water equals mass water, C water, and delta T. Well, delta T is the same for the water and the pan. We can use that twice. In this case, 0.25 kilograms instead of water, we're going to use alcohol, which is going to be a lower number.
What kind of alcohol we are using?
Don't they have it in the... Do they have more than one kind of alcohol down here? They only have one down here, which is ethanol. So we'll use ethanol. Most alcohol is ethanol. Most alcohol that you like cook with is ethanol. So 2,450, about half what it is for water. So we put 2,450 in there instead of the 4,186. All right? 2,450 right there instead in the 60 degrees. And you're going to get about 35 kilojoules of energy. So it took 35 kilojoules of energy to change the alcohol 60 degrees Celsius to heat it up. For the pan, you're going to use the mass of the pan, half a kilogram, times the C of copper, which is not 900 joules, but 300 something joules per kilogram, and then the 60 degrees. And then here, again, you're going to get about a third of that, which you're going to get about 10 kilojoules. So if you have a copper pan and you have alcohol in the pan, it's going to take a lot less time and a lot less energy to heat it up, right? So why don't we just cook everything in alcohol? Wouldn't it be faster?
Yeah, but whenever you change it over from when you're 0.25 liters of water, not equal 0.25 kilograms of...
Yeah, you're going to have different masses there, I guess, as well. I just used the same mass, but if you had 2.5 liters of alcohol, you would have a different mass. It would be lower. You're right. I didn't make that conversion, but so you'd probably have about 2 kilograms of, or 0.2 kilograms of alcohol compared to the 0.25, so it'd be even lower, right? But the point is that even if you had the same volumes of alcohol as you did to water, you would have different different amounts of heat needed to change the temperature, because alcohol is different, the copper is different, right? So why don't we just cook everything in alcohol? It's not really the issue, actually. The issue is that our food is not made of alcohol. Our food is made of water, right? We can't cook in alcohol because we'd still have to raise the food's temperature to a very high temperature. The food, you still have to put a lot of heat into food because food is mostly made of water and oils. We have lots of oils, fats, and things in our foods, and we have lots of water in our food. So to cook it in something that doesn't have very much energy in it would be useless. So we still like to cook our food in water because when you heat up water, it has a lot of energy in it, and that's enough energy to cook the food. How many of you have ever been above 10,000 feet and tried to cook something? Anybody have been here above 10,000 feet? If you've ever go up to the top of mountains,
9,500 water boils quick.
if you go to, at 9,500 feet, water boils extremely quickly. The boiling temperature of water goes way down, and you cannot cook your food very easily at those altitudes because it doesn't have enough heat in it. It requires less heat to boil the water. So the water doesn't have as much energy in it when it's boiling. And that's a problem. When you're up at high altitudes and you want to cook your ramen or something, you get crunchy ramen unless you cook it for like a half an hour. It takes that long to cook ramen up there in boiling temperatures because it just doesn't have as much energy in it. It doesn't take as much energy to boil it. So it's a problem for people it's a problem for climbing at those altitudes because you need to have a lot of high calorie foods or you just die at those altitudes. So they end up bringing up with them things like, canned food essentially. Well, they bag it, but they bring up food that's completely prepared. So all they have to do is warm it up if they want to warm it up. Warm it up if they don't want to eat it frozen. So it's a very heavy deal to climb above 10,000 feet because you can't carry it dehydrated.
Can a pressure cooker offset that?
Yeah, but pressure cookers are also heavy. If you had a pressure cooker, you could cook up there because you could raise the pressure inside and it would hold more heat. Yes, but they're very heavy and notoriously dangerous. So usually they carry like one aluminum or one titanium pot, and that's it. That's what they cook in. That's what they eat out of. They cut down on everything. Even their fork is half
Yeah,
size.
I got one of them kits, the GSI ultra light tools.
Yeah,
I take something that's this big, right?
yeah,
You do everything. You boil water, cook,
yep.
coffee.
Do everything. And up above that, up at those altitudes also, you can't cook with things like propane or anything like that because it's too cold and the pressure is too low.
GSI micro tools.
I prefer MSR and Primus because they use white gas.
Yeah, I like the MSR cooker.
Yeah,
That's
and
what my cooker is.
that's what your stove is.
Yeah.
Okay. Yeah, the MSR makes really good ones. So does Primus. I actually have a Primus Ultralight, and yeah, they're nice. Mine will burn anything. Mine will burn gasoline, diesel fuel.
Well, see, I get mine where you just put the canisters on it.
Yeah, and those don't work at high altitude is the problem.
Well, the ones do the propane butane mix.
Propane butane mix might depends on temperature.
Yeah, they work pretty good even when it's cold, right? Like
Yeah.
I set them in snow, and they.
Yeah, the cold's not so much the issue as the altitude. Like at high altitude, you won't get anything to light except white gas. It has to be like pure kerosene. So, you can do a really pure diesel fuel at those heights, but gasoline doesn't even do much at those heights. It's not so good up there. It has to be a diesel fuel and a very pure one. Kerosene. Good stuff. Anyway. All right, temperature change and heat capacity. So that's what that's all about. Temperature changes as you add heat, more and more and more heat. Let's look at a problem that relates this to another type of energy, which is potential energy coming down a hill. So as you're coming down a hill, sorry, what?
Whenever we're doing these, we've got to change it to Kelvin, too.
Whenever it says change in temperature, you can change it to Kelvin if you want, and I usually do just because then I don't ever have to worry about it. If you change it to Kelvin, you're pretty much always safe. But whenever it says change in temperature, it always means temperature final minus temperature initial. So you could also use Celsius and it would give you the same answer. But it's never a bad thing to change it to Kelvin, then you don't have to think about it. In this case, we have a truck going down a hill, and as it's going down a hill, it's going to slow down using its brakes. And we have 100 kilograms of brake material, which has a specific heat of 800 joules per kilogram. And the material is going to retain 10% of the energy from a truck descending 75 meters. So in other words, you have this potential energy of the truck going from 75 meters down to 0 meters. 10% of that potential energy is going to be sucked out by the brakes, by the heat in the brakes. So how much potential energy is that? Well, it's 75 meters times gravity times height, so 75 times 10, 9.8, which is 750 times the mass of the truck, and the mass of the truck is 10,000. So it's a big number, 750,000 joules. And 10% of that is 75,000 joules-ish. And that's the amount of energy that's going to be in this heat equation. So that'll be our Q, in other words. We're going to rearrange this equation so that the Q is on the right-hand side, so the T is on the left-hand side. We get Q over MC then this way. And the Q is going to be this 75,000, which is this right here, 750,000, I guess. So it's 7.35 million joules. We're going to take 10% of that, which will be 735,000 joules, and that's going to be right here in Q, 735,000 joules. That's 10% of the change in potential energy. We divide it by the mass of the brakes and the specific heat of the brake material, and this will tell us how much change in temperature those brakes will experience. 9.2 degrees Celsius change in temperature. Not bad. You figure you're going from outside temperature, which is 25 degrees Celsius, 9 more degrees, 35 degrees Celsius, not a big deal, right? No big deal. But you have to know that. What if it was 90 degrees Celsius change? What's the problem with that? Well, what are the brakes up against when they're braking? They're up against steel. And steel has a much different specific heat. And the steel is going to get that same amount of energy in it, and it's going to raise its temperature a lot more than 90. And steel melts when it gets too hot. And that happens with brakes all the time. You can melt out your brakes, especially if you don't have a very big mass. If your mass is small or the brakes are thin, that's when the mass of brakes gets small, is when they get thin. Then it can't handle that heat anymore and it will start to melt. It will raise its temperature very quickly and the brakes will melt. So this has to be known before you design brakes. And when they're looking at the thickness of your brakes and the thickness of your brake pads in your car, that's exactly what they're trying to avoid. You want to have a thick brake pad so that it can handle the heat, and you want to have a thick brake drum or brake disc so that it can handle the heat. Has nothing to do with anything else. Has everything to do with handling the heat. On the back side of your disc brakes, well, at the bottom side of your disc brakes, there are those vanes. You ever wonder what those are for? Well, they just add mass to the brake, actually, so that that heat can go into this other part of the mass and be distributed a little bit. And the vanes help that heat to be carried away. It allows wind to get in there and carry that heat away so that it keeps the brakes cool. So there's holes in your brakes for the same reason. The holes in the brakes, in your brake discs, are there for the same reason. It helps them to cool off. It helps air to flow in there. It helps them to cool off. Brakes are actually more efficient if there aren't holes in there. But if there aren't holes in there, they don't cool, and then they are not so great, right? So they make compromises. So that is the idea behind heat and how it changes the temperature in a material. The problem is that heat doesn't just change temperatures in materials. It also changes the way the material behaves. For example, if you melt your brakes are no longer solid. And then they behave differently, right? Your brakes are now liquid or partially liquid, and they have a very different behavior pattern to them. It's like having a completely different material. And when they do that, when they change from a solid to a liquid, or a liquid to a gas, or a gas to a liquid to solid, whatever we call it, a phase change. And the interesting thing about phase changes is while the phase is changing, it never changes temperature. So last week when we filled that bucket full of ice and water, the ice was melting in the water because the water was a higher temperature than the ice. But the ice was also cooling off the water, because it's colder than the water, of course. So they were cooling and heating each other at the same time. But eventually they would get to a point where they were at a temperature where neither one of them could cool the other one off or warm the other one up. That's what we call equilibrium. And there would still be ice and liquid left if we didn't start off with too hot of a liquid. So it's at an equilibrium, where they're at the same temperature. And that's kind of like what happens when you start melting ice. It stays at the same temperature, and it stays in that equilibrium state where you're putting heat into it and you're melting ice, but the melted ice that becomes liquid stays cold because of the other ice there. The other ice cools it and it melts more ice. And until you have all of the ice gone, it's going to stay at that one temperature. And for ice water, it happens to be 0 degrees Celsius. 0 degrees Celsius is the transition point between liquid ice and solid, or liquid water and solid ice, or liquid water and solid water. And every material has these points. They're different for every material, but everyone does have it. Here are some of those points. For helium, the boiling point is negative 268.9 Kelvin. It's like 5 degrees Kelvin, right? It's where helium goes from its liquid state to its solid state. It's almost as cold as it can be. No, from liquid to gas, rather. That's where it goes from liquid to gas. Solid helium is much colder than that. So the boiling point, that's where it becomes a gas from a liquid. Hydrogen, pretty close to the same temperature. Really, really cold is where it becomes a gas. That's pretty much why those are always gases. Nitrogen also very cold, but not nearly so cold. Only it's about 100 Kelvin, 70 something Kelvin, 78 Kelvin. Oxygen also quite cold. Ethanol, the boiling point is actually up close to the boiling point of water. The boiling point of water is 100 degrees Celsius. The boiling point of ethanol or alcohol is 78.3. The boiling point of lead is 1750, 1750 degrees. A temperature easily achieved on a stovetop at home. You can easily get to that temperature on your stovetop at home. I don't know how many of you have melted that one.
I haven't done it on my stove top.
I have. I've done it on your stove. You can know already. No. Lead is easy to melt. That's an easy temperature to reach on a stovetop. Sulfur, even easier to boil off sulfur. Mercury, 357, much lower, much easier, right? It'll boil at 357 degrees and become a gas, essentially. Tungsten, not so easy to melt. Uranium, not so easy to melt. Copper, not so easy to melt. This is why we make our pans out of copper. Aluminum, not so easy to melt, although you can melt it. It can be done, and it can be done at home. You can get an aluminum pot hot enough. No, you probably couldn't do it with your home oven, but you could do it. I mean, I've done it before. We did it in the laboratory.
I built a flower pot foundry. My dad and I used to melt down cans and cast ingredients.
Yeah.
We used a hairdryer and some charcoal.
Yeah, it doesn't take much. You can do it in a simple time. But very difficult to melt and boil some of these other ones here. It gets very, very difficult. But here's what happens as you start adding heat to something. This particular chart is for water. When you have water that's very, very cold, below 0 degrees Celsius, it will be ice in normal pressure situations. And so, but ice can be colder than 0 degrees Celsius. Your average freezer is usually 20, 30, 40, 50 degrees below zero, below freezing. So it keeps it colder than freezing. If you have your freezer at 0, things will be all melty in there. But it's not quite cold enough to keep everything cold all the time. So you want things to be quite a bit below freezing in your freezer. So when you take ice out of your freezer, it's really low temperature. And it may take a while for it to start melting. It really has to absorb a fair amount of heat. Because at first, what it does is it just changes temperature. Ice that comes out of your freezer when your freezer is cold, the first thing it does is it just changes temperature as the heat is added to it. It doesn't melt. But eventually, it'll get to a point where you'll start having a mixture of ice and water. You have water sitting on top of the ice, cooling around the bottom of the ice. And that is where you're going through phase change. And that is when you will have 0 degree ice, and the water that is in contact with that ice will also be 0 degrees. And it will be 0 degrees for a little while. What we've got down here is the heat being added. So if we add 20 or 30 joules of heat right here to a kilogram of ice, it'll change temperature during that time. But if we add another 80 joules of ice, then it will melt it to that 1 kilogram of ice. Then if we continue to add heat to it, it'll change its temperature. And the temperature will go up and up and up and up and up until we get to having added about 200 joules of energy to this 1 kilogram of glass. We've gone from negative 20 degrees now to 100 degrees Celsius. And we've added about 200 joules. Is it joules or is this calories? It's actually calories. 200 calories. We've got about 200 calories per gram, so it's about 2. Well, it's energy. Right. But once we get to this point, the water starts to boil, and you're getting gas and liquid together. And it goes through another transition phase. But this transition phase takes a lot more energy to get through it. It takes all this energy. You have to add all this energy from here to here to boil off that water. Now, this is why steam is so dangerous. Can you even see that? Okay. This is why steam is so dangerous. You add all this energy to make that steam, and all that energy is in the steam. Okay? Now, I'm not talking about the stuff you see coming off the top of your coffee cup. That is not steam. That is liquid vapor. It's essentially liquid water that is just in small little droplets in the air. The steam part is when you're making hot water in a steam pot or a teapot or whatever, and right when it's coming out, that little part where it squirts out and makes a little whistling sound, right where it comes out, there's this little spot that you can't see anything. There's a little gap. Let me show you what it looks like. So right here, see this? Actually, it's better seen. Where's a really good image of this? That's a decent one. So right here you can see that, I guess it's not that great. This one's better. You can see there's this little gap here between the pot and what we call the steam. This is liquid water vapor. This is actually a liquid, not a gas. It's just little droplets. It's like a cloud in the sky. Just little droplets of water that have attached themselves to dust. And it's liquid again. It's hot. It's probably 100 degrees or close to it. But it doesn't have all the energy that this stuff right here has. This stuff right here, where there's this little gap, that's the gas. That's the steam. Don't ever put your finger there. And if you've ever opened a pot of hot water, a pot of boiling water, that first little burst of stuff that burns your hands, that's the steam. And it's extremely hot, high energy. And if it's at high pressure or at high speed, and this is high speed, it's got so much energy in it because it takes so much energy to boil water off. That can give you a third-degree burn right away. Okay, they use that stuff to cut through steel and through concrete and all kinds of stuff. Put it at high pressure and release it. It is dangerous because it's got so much energy in it. That's the accumulation of energy during this phase change. This huge amount of energy that you pump into it to turn that water into steam. And then once it's into steam, you can get it even hotter. You can heat it up then. And you can even add more energy to it. But most of that energy was added in during that transition phase. Okay? So it absorbs a ton. And all materials do this. They have a similar chart. Not all of them have, these long paths of energy. Not all of them have this super huge amount of energy that you're adding in from the place where it starts boiling to the place where it ends boiling. But they're all different in the length of time that it takes to do that transition. But they all have these kind of transition graphs where you have an ice and water transition and a water and steam transition. But the problem is that we already have an equation that tells us how much heat it requires to change something's temperature. That was that specific heat equation. Now we need an equation that's going to tell us how long it takes, how much energy it takes to turn something from a liquid to a gas, or from a liquid to a solid, or whatever. How much energy that requires, and so we have a new equation for that. And this equation is called the latent heat equation. Now there's two versions of it, one for melting and freezing. So if you're going from solid to liquid or liquid to solid, you use this one. But it's the same equation for going from gas to liquid or liquid to gas. But it's just you use a different L. This L here is called the latent heat of fusion and the latent heat of vaporization. Latent heat of fusion is for melting, freezing. Latent heat of vaporization is for boiling and condensing. And every material has its own latent heat for this. The M is, of course, mass. But to calculate how much energy requires to change phase, you have to use this chart with the latent heats. We have one that uses kilojoules and one that uses kilocalories. But we do have these latent fusion numbers and latent vaporization numbers. And then they tell you the boiling point and the melting point, or could be the freezing point also, if you want to call it that, and the condensation point. So for helium, it's only 1 degree apart, right? Negative 269.7 is where it freezes, and negative 268.9 is where it boils. There's not much room in there where it's a liquid. It's a solid or it's a gas, and that's similar for many of these gases. They're not very far apart in their freezing state and their liquid state. Excuse me. As we get up to the materials that we deal with on a more regular basis in liquids and solids form, it starts to come a little more into our realm of experience with water and 0 degree melting point and 100 degree boiling point and other things like that. So for example, sulfur melts at 119, so you can do that on your stovetop. And boils at 446, and you can also do it on your stovetop. Lead, a little bit higher, both melting point and boiling point.
I was thinking correctly on aluminum. I was thinking melting it, not vaporizing it.
Yeah, melting point of aluminum 660, which you can achieve you could achieve that in your kitchen. Kitchen stoves are designed now not to go above 600 Celsius, so that because many pans are made of aluminum now. It didn't used to be that many were made of aluminum. So they're designed, especially electric stoves. Electric stoves can get extremely hot, but they're designed now essentially to burn out below 600. So the stove itself cannot reach that. Older stoves could. Silver, gold, copper, uranium, of course, this just goes up and up and up. But each one of these has a latent heat. So you look here and you see which ones are harder to melt, which ones are harder to boil as far as how much energy you have to put into them. Well, here you have lead, which requires 224.5 kilojoules per kilogram. So it actually doesn't require a lot of energy to melt lead. Look at ethanol. Alcohol, it seems like, could be easier to melt ethanol.
Why does ammonia not have a number?
Ammonia does not. For this one, for kilojoules, I don't know. Good question. Should have one. It's a typo or something. But anyway, up here at ethanol, though, it takes a lot more energy to heat up ethanol. That means that its line in this chart, its phase change chart, is longer here. For lead, it's really short because it doesn't take much energy. But for ethanol, it takes a lot more energy to melt it. Ethanol does freeze into a crystalline state, a solid state. So let's use this equation in an example here. We've got some ice cubes that we're going to use them to cool off a soda to 20 that's at 20 degrees already. They tell us the mass of the soda. They tell us the ice initial temperature is 0. They tell us the mass of each ice cube, and they assume that the soda is kept in a foam container, so all the heat that leaves the ice cube goes into the soda. Now I like to draw pictures when I do these every time. I keep forgetting that we're recording this, so I need to draw my pictures where they can be seen. So let's draw my pictures where they can be seen. Okay. So I like to draw pictures with every kind of physics problem, but particularly these because you need to keep track of the energy, where it's going, where it's coming from, and all that. So I've got my cup of soda, and it's got some mass of the soda, and it's got some temperature of the soda, whatever else. And then it's going to be added to, we're going to add to it some ice cubes. They said 3 ice cubes. 3 ice cubes in here. And there's going to be some mass of the ice cubes and some temperature of the ice cubes. And what's going to happen is we're going to get some Q that's going to go from one place to the other. Which way is the heat going to travel? Naturally, heat likes to travel from what to what? Not from cold, from hot to cold. So in other words, the heat is going to flow from the soda to the ice. And the heat that the ice gets from the soda is going to do what to the ice? It's gonna warm it up. But since this ice is at 0 degrees, what happens to ice at 0? It changes phase. It doesn't actually change temperature, right? At 0 degrees, at the melting point and at the boiling point, change in temperature doesn't happen. What happens is change in phase until you've melted something, and then it changes temperature again. Since we're at a solid state and it's at 0 degrees, we're going to change phase. So the heat's going to come from here and go to here. We're going to change phase. How do we calculate the heat that's going to leave here? Well, what's going to happen to this? This is going to change temperature, right? The soda is going to change its temperature. The ice is going to change its phase. So I like to write that. I like to write we're going to get a change in temperature here. And here we're going to get a change in phase. And why do I write that? Because that means different equations. The change in temperature equation is Q equals mc delta T. This will be m of the soda times the C of the soda times the delta T of the soda. But change in phase is Q equals, for melting, the mass of the ice times the latent heat of fusion of the ice. And these two Q's have to be what? They do, because the heat's coming from here and going to here and it's not getting lost in between. So these two things are equal. Right? So that's the whole problem right there. MSCS delta TS equals MILFI. And the thing that they're trying to add, let's see, what did they give us here? Where's the problem? It's over here. They give us the 20 degrees. That's the initial temperature of the soda. They tell us the mass of the soda is, so assume the soda is kept, find the final temperature. They want to know what the final temperature is. So if we calculate delta T, we should be able to find the temperature of it. The temperature, when all the ice is melted, that's before we start heating up that water that was the ice, and we can figure out what the change in temperature is of the soda at that point. So we want MSCS delta TS, and let's go see if that's what they give us. They're saying the Q of the ice is going to equal negative Q of the soda. That's just because it goes in and one comes out the other, and that's fine. So they're going to have, they write it in two different ways because they're talking about, they say here, well, the change in temperature of the ice. Well, the ice doesn't change temperature, so that ends up being 0. And they end up solving the same equation, m times L times MC delta T, which is this one right here, MC delta T. So MCT and M times ice, and then they're doing it slightly different. Then they take a difference, and that's fine too. But either way, they get a temperature, a final temperature of 13 degrees Celsius. I would have gotten a change of temperature of -7 doing it my way, and it would give you the same answer. So that's the whole idea of this, pretty much this chapter. Everything else is about heat transfer methods, which is what we'll talk about next. But what you want to do here is you want to be able to set up equations for the heat entering, leaving one thing and entering another thing, and either changing the temperature or changing the phase. And it could do both. You could change the phase and then change the temperature if you have enough heat, right? Let's do another example, if there's no one. Well, this is a great example here. Okay, so peach trees are notoriously susceptible to frost. It damages them very easily. Okay? And if you damage your peach blossoms in the spring, you get no peaches. Right? So in Colorado, where they like to grow a lot of peaches, because we can't grow peaches in Nebraska, but we like to eat them in Nebraska, so they grow them in Colorado and bring them up here. They have good weather in southern Colorado for peaches, except for a few days every year. A few days early in the spring, when those blossoms have already come out, they'll get a frost day. So what they do is, they used to just flood their fields all the time. But nowadays, when there's a forecast for frost, they'll go out and flood their fields with water. In the morning, the water's frozen, the peach blossoms are in great shape. Why?
Because it takes more energy to freeze the water than it does is all the energy going to freeze the water or what?
You're close. What happens when a liquid freezes? Does energy go into it or does energy leave it? Where does that energy go? Up. It just leaves, right? So if you have a bunch of water at the bottom of your orchard that's freezing and losing energy, where does that energy go? Up into the trees, into the blossoms, and those blossoms love it. Now the blossoms are nice and toasty warm even though they're above a lake of ice. Right? So it turns out that freezing is actually an exothermic process. Freezing releases energy. Why is it that when it's snowing outside, it's usually never nearly as cold as when it's clear outside? Because as the water in the air is freezing and making the snow, it releases energy, and it makes it warmer outside. Snow almost always comes with warmer temperatures. And it's not because it snows when it's warmer, it's because it gets warmer when it snows. Right? So it's a great thing. And so they actually use this to their advantage. It's not something that they just figured out a couple hundred years ago. They've been doing this for 1,000 years. They figured out a long time ago that flooding your orchards will preserve the blossoms. Also, you can actually spray the trees with a mist. And that's done all the time in agriculture. You spray it with a mist and the energy is released and it will go inward as well as outward. And it will preserve and it will also actually kind of insulate from further cold. So that's another process that's used. Okay, now. Heat transfer methods. How does heat go from one thing to another? Well, there's three ways. By touch, we call that conduction. By movement of fluid or liquid or air, that's what we call convection. And by radiation. There is no mathematics that we can do associated with convection. Convection does have mathematics, but it's extremely difficult mathematics. Conduction is actually fairly easy. That's the one that we'll talk about. That's the two, well, one of the two that we'll talk about. Heat conduction happens from just having two materials in contact with each other, and one of them warms the other one up, the other one cools the other one down, and that's fine. But the heat travels through the material because of the contact. So the amount of contact matters. The area of contact matters. So if you just touch somebody with your finger, you're not going to warm them up. But if you put your hands around their hand, because they've got cold hands, you're going to warm them up more quickly, much more surface area. Also, the difference in temperature matters. This is something that Newton figured out a long time ago. The bigger the temperature difference between two objects, the faster the heat travels. So this is a really interesting thing for efficiency in heating your house. Most people are convinced that if you keep your house warm all the time, it's very efficient because then you don't have to heat it up when it's cold. But it's actually more efficient to turn your heater down during the day when you're not there and turn it up right when you get back, because it will very quickly heat. It will take literally minutes to heat and will require less energy than keeping it warm all day. Because the bigger the temperature difference, and your heater is always at one temperature. There's only one temperature that it goes at. Even though you set the thermostat, when it turns on, it comes on at one temperature. So that the difference in the temperature between your house and the heater makes for a more efficient and more quick heating cycle. So it's more efficient to turn it down than to just keep it at a constant temperature. It's also healthier. So here is the rate of conductive heat transfer. That's heat divided by time. So this is an amount of heat traveling through from one material to another in an amount of time. Is directly related to the area A that it's traveling through, the temperature difference, delta T here. It also is inversely proportional to the distance. So if it has to travel through a long distance of material, then that makes the heat transfer less efficient. So divided by D, and then it's multiplied by this heat conductivity, this thermal conductivity constant, K. Every material has a different thermal conductivity constant. And so in this example, we have a styrofoam box that has this area, that's the A. It has a thickness, 2.5, that's the D. It has a temperature on the inside, 0 degrees, and a temperature on the outside, 35, so there's your difference in temperature. And then styrofoam has a K constant, and they have a thing of K constants right here. K constant for styrofoam is 0.010 for styrofoam. And so that's a really good K constant, right? You look at other things that we use for insulation, glass wool, for example, which is what you have in most houses are glass wool, fiberglass, 0.042. So styrofoam is 4 times better at blocking heat than fiberglass. But look at air. Air is almost as good as fiberglass. It's way better than this. Why don't we use air to insulate our houses? The air cannot be moving and it cannot be replaced. It essentially has to be an air gap. And so air is quite good in insulating, but only if it doesn't move. And that's hard to... That's why those triple pane windows work good, but that's also why fiberglass is used, because fiberglass prevents air in the walls from moving very much. So that's the reason. If you could do your whole house in styrofoam, you'd be in good shape, but styrofoam insulation is very expensive. So also styrofoam is flammable, whereas fiberglass is not. Anyway. So anyway, you've got all the numbers and you just plug them in here. In this case, they want to know what is the heat, how much heat is going to travel per time. You plug in all those numbers they give you, get 13.3 joules per second. And then they want to know how much it's going to take in a day, so you how much heat is going to go through in a day, so you multiply that Q over T by the number of seconds in a day, which is 86,400 seconds, and you get this much heat lost every day. Then you can actually say, well, how much does heat cost? And then you can figure out how much it's costing to heat your house. We're losing 1,000,000 joules of heat per day out of this house. How much does that cost? How much, in this case, they ask, how much ice could you melt with that? You could melt 3.4 kilograms of ice with that. And that's like 10 pounds of ice-ish. 7 pounds of ice. So that's conduction, heat conduction. The amount of heat that travels through material in a certain amount of time can be calculated by a change in temperature and area, distance, and the constant. It's pretty simple. Convection, like I said, there's no way to measure it using the math that we use, but it's still very interesting. Convection methods are used in so many different places to heat things. So in your house, whether it's a furnace or a fireplace or baseboard heaters or whatever else, all of these methods use convection to heat the house. Why do we put the heater vents at the bottom on the floor? Most houses have your heater vents on the floor. Some houses put them in the ceiling, especially on the top floor. But if you really want to do it right, they should always be in the floor. Because in the floor, you get hot air coming out of your heater that rises naturally in the room, which displaces the cold air at the top of the room and pushes the cold air down towards the bottom. And you also put in your intakes for the cold air at the bottom. Now, some houses, again, put your intakes at the top. You can do that because then it sucks cold air out and heats it up very quickly. That's not a bad way to do it.
Change it. You're supposed to, in the summer, you're supposed to do it one way, and in the winter, you're supposed to do it the other.
It would be ideal if you could have different vents for heating and air conditioning, but we usually don't, right? So you make a compromise, and you try. So what people do is they'll put their intake vents at the top of the house and their heating vents at the bottom. That way, in the wintertime, it's ideal for heating because you got the hot air driving it up to the top. In the summertime, you want to drag the hot air into your intake vents. So in the summer, the intake vents are ideal. So that's what most houses do. You put your intakes at the top so that you kind of split the difference. You could do it the other way and split the difference. It depends on which parts of the year are most uncomfortable for you, the summer or the winter. But the point is that you're actually creating this convection. You're actually encouraging this convection through your house. And you want the hot air to displace the cold air in the wintertime. You want the cold air to displace the hot air in the wintertime so that it cycles through this system. And that's how convection works. That's the idea of convection, is the movement of fluids or gases to encourage heating. Now, one of the things they talk about when they talk about convection is they talk about the wind chill factor. They also talk about convection in fur, right? So particularly, my favorite is polar bear fur, right? What color is polar bear skin? No, it's actually black. So it actually the polar bears use 3 different methods to heat themselves. They have this black skin. We'll talk about how that works later. But their fur is actually what color? It's actually clear, believe it or not. So their fur looks... Yeah, their fur is actually clear. If you look at it very closely, if you take a bunch of polar bear fur and you spread it out on something like black, you'll be able to see through it. It's actually clear. It's like little pipes of glass. It's like little tubes of fiber optics. And it's hollow as well. It's hollow fur. But the beautiful thing about it is it's very fluffy, so it allows convection. Their warm body, which has this black skin, is making the fur near their body really, really hot. And that rises out towards the end of the fur and creates this heat layer between them and the cold air outside. But they also use, they're also using, so that's the convection part of it, but they're also using radiation. So the light from the sun gets inside this tube of fur, and it bounces around in the tube, and it goes all the way down to their black skin and heats up the black skin. The black skin absorbs almost all of the sunlight and turns it into heat on their skin. And then that, again, causes more convection outward. So polar bears are extremely efficient at keeping themselves warm because they use all 3 methods. They use convection, conduction, and radiation to keep themselves warm, all in one thing. So they look white, but they're actually black, and their fur is not even white. Their fur is actually clear to allow that sunlight to get through very well. So it's really interesting. It looks white because of all the light that scatters off of it. It scatters the light so perfectly that it scatters every wavelength of light and looks white. It's really interesting stuff. Here's an interesting problem. We have a person who's getting really, really hot every day, but the conduction between their skin and the liquid on their skin, the sweat on their skin, is causing the skin is causing the heat. The heat is evaporating the sweat on their skin. There we go. And so you have this heat, which is this heat per time, this energy per time, which is 120 watts. So that's the Q over T, 120. And that's going to evaporate water, which is slightly salty, but we're just going to use water. and that's m times LV, liquid, the latent heat of vaporization over time. And it's going to be 120 joules per second, 120 watts. And we want to solve for how much mass you're losing per second in sweat. We talk about sweating things off, right? If you're sweating things, this is what happens if you're sweating things off. So you have mass per time, 120 joules per second over latent heat when you solve this equation, or the latent heat of vaporization. Latent heat of vaporization for, let's see, I guess they're using for sweat, not for water, is 2430, so 2,430 kilojoules per kilogram. And so they plug in those numbers, and it's 2430 joules per gram as well. They plug in those numbers and they get 0.0494 grams per second. So you lose 2.96 grams per minute of sweat when you're doing, what are they doing here? Oh, so this is just normal. This is how much weight you lose just by sweating, right? 2.96 grams per minute. How many is that in a day? 180 grams per day, so that times 20, it's 200, so it's 4,000, 40,000. No, that's not right. 7 ounces per hour, that's easier. 7 ounces per hour, so you're going to lose a couple of pounds a day just sweating. Probably 5 to 10 pounds a day just sweating on average. That's pretty good, except that you're eating 20 pounds of food a day. Maybe not 20 pounds of food. But let's see, what do we do? We're drinking, so if it's 7 ounces per hour, 20 is 140 ounces. So that's about almost 10 pounds, right? Almost 10 pounds a day of sweat. And we drink in, we're supposed to drink in at least a half a gallon a day. And most people do drink in liquids on about a half gallon of liquids or a gallon of liquids a day. And then you eat another 10 pounds a day. So that we're either maintaining or gaining weight every day, right? People think that you lose weight just by burning energy, but that's not technically true. You don't lose weight just by burning energy. Most of your weight gain and loss every day is liquid gain and loss, not energy burning. And energy is not converted to mass, and mass is not converted to energy in our body. It just isn't. So we break bonds in the food that we eat. We break those bonds, and those bonds have energy. But using that energy doesn't cause us to lose weight, except that it causes us to sweat. And when it causes us to sweat, that's where we lose the weight. So, I love the perfect example yesterday. There's a group of faculty members that do a lot of walking around campus. You've probably seen them. And they do a lot of walking, but yesterday there were 2 different situations where you could get free cake and free cookies. So during their walk, they're eating cake and cookies. I'm sure they're thinking it's okay because I'm walking. The problem is that cake and cookies are full of fat. And fat almost never goes through our system. It doesn't just go through our system, it gets stored in our body. And when something gets stored in your body, it takes forever to get it out of there. You want foods that will go through your body very quickly and very easily. Carbohydrates go through our body very quickly and very easily. People that say on a high protein diet, I'm going to lose weight. Ridiculous. High protein diets are almost always high fat diets, and they almost always get stored in the body. And so you got a problem there when you don't eat foods that just move through the system. They got to move all the way through your system without stopping and getting stored if you want to keep your weight at a decent level. Things that are high in fat, cakes and cookies and things like this, they're just made with, the primary ingredient is lard and fat and butter, which makes them taste delicious, but they stay in your body forever. Carbohydrates are great for losing weight, as long as you're exercising. What's that? Let's look at one more problem here. One more thing here and we'll be done. So radiation, what is radiation? Radiation is things that heat up because light is hitting them. Light in many different forms. It can be infrared light, it can be ultraviolet light, it can be all visible lights, it can be anything. Things absorb electromagnetic radiation and then they heat up because of it. It can be X-rays. X-rays can make you hot. Anything. And this amount of heat is governed by this equation called the Stefan-Boltzmann law. It again has to do with an area, how much area is exposed, but the temperature is a temperature to the fourth. So the temperature of the object that's emitting the heat is a real big factor. That's why the sun radiates so much heat, because it's so hot. There's such a high temperature to it. Temperature of the sun is extremely high, and you take that temperature and multiply it by itself 4 times, and that'll tell you how much heat that's given off, right? But then you also have these 2 factors here. One's called the Stefan-Boltzmann constant, which is just this number, and the other one is the emissivity of the material. Everything has an emissivity. Some things have an emissivity that allows them to essentially reflect everything that hits them, like a mirror has an emissivity that reflects. Where are the emissivity numbers? They'll tell you, I guess they'll tell you the emissivity. But an object that absorbs everything that hits it has an emissivity of 1. And an object that reflects everything has an emissivity of 0. So an object that reflects everything that gets shown at it perfectly will not emit any heat from its radiation. But one that absorbs everything will. The sun is almost a perfect black body. It's almost a perfect radiator of heat. So is the Earth, actually. The Earth is almost a perfect black body. They call them black bodies because if they don't have any light shining on them, they will look black. Well, not entirely true, but anyway, it's because of their spectrum. But here you can see the interesting thermograph of this building here that shows you how much heat is coming through by radiation. This is how much infrared radiative light is coming off of things. And you get the windows, which are this bright yellowish color, and the walls that have bright yellows. But then some walls are blue. This would be a colder part of the building, blue and green. There's obviously no heat up here, right? The hottest part of the buildings are actually these pink parts. Heat's coming out in droves at these parts, or they're being heated up by the sun or something else like this. So, interesting stuff. So in this example, they tell us the heat transfer by radiation of an unclothed person standing in a dark room, temperature 28, 22 degrees, the normal skin temperature of a person 33 degrees, their surface area. And so you take the temperature difference here and use that as your temperature of the radiator, and you raise that to the 4th power. You have to actually raise it to the 4th power and then take their differences. And then that'll tell you how much energy is coming off of that person in radiation. Turns out to be 99 watts. So we actually radiate a lot of energy out of our body as well. Our bodies don't just sweat off energy, we radiate energy. And this is why you can use night vision scopes to look at a person, because we're giving off constantly this infrared light. It's not just infrared, we also give off some near microwaves and things like this, other things. We also give off just other lights, but most of it turns out to be infrared. And those things can be detected by certain devices. So, I actually have a camera that's designed that I modified several years ago. I wonder where that is. I modified a camera several years ago so that it would detect infrared light instead of detecting visible light. So maybe we'll try to go find it. But anyway, this is the end of the chapter here. I don't have anything else in this chapter. I didn't give you any problems from this chapter, but I will. I'll tell you what. Well, let's do this one, the same heat transfer You know what I'm going to do for you? I'm just going to copy these into Word for you really quick. And I'll just email them to you. That'll make it easier, won't it? So here's the first one. And this one. And this one. Let's see. Okay.
What's the format of the actual game going to be? Is it going to be online like the rest of them, or
What's that? Sorry?
the format of the last exam?
One more time?
Format of the final exam.
Oh. It will be partially. Um, it'll be partially my open math stuff and partially written like this. I like the walrus one. Yeah, gotta have the walrus. Okay. And then radiation. Let's do one radiation problem.
We just emailed.
Yeah, I'll email them to you. Yeah, go ahead. Yes, happy Thanksgiving for sure. Frozen waste from airplane toilets. Sometimes been accidentally ejected at high altitude. That one, you got to do that one. That's a great one.
Has there been people killed by that?
That's just got to be the worst thing to have in your death by frozen excrement.
Yeah. Walking down the street, wham. So why did the girl get kicked out of her? Got the email about this?
The basketball player?
Yeah.
I don't really know any of the details. I heard there was some kind of an altercation, but I don't know much besides that. Well, let's do. Here's a car radiator problem. Okay, so each page is its own problem. There are, how many pages? How do I get rid of this? Ten pages, so we got 10 problems from here. And I will email this to you.
Since we've got 7 chapters, there'll be 70 problems.
The final will never have more than 2 questions from a chapter.
And then you're gonna have to do each one.
The final exam will be, let's take a look at it actually. Let me send this off to everybody really quick. That's I've sent something to all of you before, haven't I? At some point? I thought I had. Close. All right, let's just do it here. Um, is one of these yours? No. What's yours? What's your email, Mueller?
I don't know which email I got,
I
but
don't
it's ZM.
S Taylor 4454.
know. ZM what?
ZARIC MILOS at gmail.com.
Like that? Z Medic Milos?
You just missed Z after M. Z after M. Yep.
Alright, mine is Scott.max.taylor.
Scott.max.
M-A-X. Dot Taylor. T-Y-L-O-R at gmail.com.
Who am I missing? John?
Field.
What's John's last name? Is it Connor? Can't remember. I'll go look. Taylor. No, that's Scott. John Schroeder. That's right. Schroeder. Here we go. Now I got it. All right. Here we go. Attach. Okay. That is coming to all of you at this point. So this is what the final exam is going to look like. Let me give you a little preview. Final exam. So there are 9 questions. Is that right? This is definitely not. That's way too many. There's 9 questions from previous stuff. And then there is one question that has, I thought that I even put that on there. Yeah. So I've added at the beginning 4 questions. These are different ones than I'll use because I gave you guys different questions than I gave my other class. But I'll add probably, I might add 5 or 6 questions from the chapters that we did the homework. Oops. But I'll add them at the very beginning, the ones that you do by hand. Does that make sense? How that will work? There will be no more than 20 questions for sure, but probably about 15 questions is usually what it's about. Oh, that's kind of crazy looking. Is that the gunship you were talking about?
Spectre.
C-130.
The Spectre.
It's a C-130 gunship. It's just loaded with
It's got the
cannons
same
and
turret and aiming system as M1A Abrams tank in it.
yeah.
Yeah, so it's the AC-130.
All right, so that's where we're at.
The optometrist to pick up glasses, so I'll actually be able to see tomorrow. It'd be amazing.
I haven't had new glasses in a few years. I'm due.
This
These
is
ones
my
are getting
backup
thrashed.
pair. They're 7 years old, chipped, and apparently the prescription for the left eye is off by about 0.5. Which explains why I've had to sit there for the last so long. Have a happy holiday, folks.
You too. Happy Thanksgiving. Did you guys ever figure out what you're doing for Thanksgiving, or do you guys need a place to go for Thanksgiving?
So maybe we're gonna stay here because I need to prepare for this meeting.
How many of you are staying?
I think just me and Nico. I
Dude.
go for Brazil.
Well, if you guys need a place to eat, you come eat with us. My little brother is coming from Rhode Island. My daughter is coming home from college. My daughter just got her first boyfriend ever.
Ain't that exciting?
What's that? I met him as a child. His father was one of my professors. Well, she works at the physics department where I went to school. So they actually, she probably met him too, at least in passing. They went to the same functions together when I was a graduate student there. Her dad is a professor. I think he's got 15 kids or something crazy like this. He's got a huge family. Yeah, because his oldest kids are my age.
How old is this guy?
This kid's the same age as my daughter, early 20s. So, yeah, got a huge spread of families. It's not abnormal to have a big family when you're a Mormon, but 15 is a little out there. It's a little on the edge of things. But
You said it's Mormons don't like to get busy.
that's right. No Mormons say that, I can tell you that much. They get busy and they keep busy. It's funny. Oh, anyway. I'm going to take a little bit of a break right now just so I can get up and walk around, but I'll be back to help with homework in a little bit.
The
Which one?
one that got thrown off out of the school.
I don't know. This school here,
Yeah.
I don't have any idea. I heard that they're talking about, but money you need to spend to go to Canada. You need to get some license.
Yeah, the
So you
license,
find out.
the license that I bought was $280 it's for a cow. It's not for a You wanna go, I'll take you next year, you know. I will even bring you back.
How far is it from here?
700 miles. Or, yeah, I'll send you all pictures.
That's perfect. Certainly, it's pretty expensive to go to Japan. You get the license first.
Yeah, and then you gotta deal with the force meister, you need the guns, you gotta have the class there too, and you can't just go hunting like it is here. They just tell you what you can shoot. Yeah, I spent some time in Germany, man. Always from Germany.
Yep. And you have more, like, restricted content in Serbia. Because in Serbia, a lot of people hunting illegal.
In Serbia, it's illegal?
For some periods of year, and some people doesn't care about it.
Yeah. That would be me.
You guys have any questions?
Oh my lord. So, if I get everything lined out, because they're gonna work 16 hours Thanksgiving and 16 hours the day after Thanksgiving. Yeah. That's kind of what my days look like those 2 days, and then all weekend.
So your Friday is truly a Black Friday.
Yeah, but if you take 35 times 1.5, which is $50 an hour, times
Not bad.
32, plus another 16 times 50, that's how much money I'm gonna make in those 2 days.
More than I would make those days.
So here's
Of
my
course,
question.
in those days I don't work at all.
Yeah. Oh, my chair, my share. So I was gonna come in tomorrow at 10 o'clock to spend an hour or an hour and a half with Miss Becky. So, is there, do you want to come in tomorrow?
Do I want to come in? Yes. I will come in if you need help.
I'm trying to get as much of it. I'm trying to get as much of this stuff ironed out. Like if I can have everything in
If you want to come in tomorrow and work on physics, I can do just tell me what time. You want to come before you work with Ben, or you want to come after?
What's better for you?
I like working in the morning, but whatever works, I don't care. Like I could be here at 8 o'clock, and I'm going to do 8 o'clock, if that's too early to do after.
Later.
Well, the land, I can start to work on this homework. And I don't have any question because I didn't even start to work on this.
Yeah, we can do 8 o'clock tomorrow.
I'll be over here about 8, 10, 8:15.
I'll bring my little brother now too.
Okay. Is he a physicist?
He's an engineer.
Oh, okay. No, I don't have engineer.
He's smart too.
It's like the Big Bang Theory. Sheldon, you ever watch the Big Bang
Oh,
Theory?
yeah. It's a funny show, and the physics is really good. They get good science in their show. I don't know about biology or anything else in the show, or chemistry, but I know the physics is good. Ugh. Yeah, that's a great show.
This weekend we run different solutions to different pumps to imitate agitation. And then we found this one type of pump which is JD Plummer solution.
Oh, yeah.
This is our physics class.
Here's some pictures.
That's cool. Is it because it's mixing with something?
I don't know, but we need to
Figure
see
it out.
today from manufacturer how it works and everything.
Oh, that's interesting. On Monday, I'm going to meet Darren. You know Darren?
Yeah, I know.
I don't think I've ever met him. Maybe in passing. But he and I are going to talk about me possibly doing some PhD work with him. So I might come soon.
Why did you choose him? I think he's working with irrigation.
Because technically he's an engineer. And he does a lot more of the engineering side of things. It would be either him or your guys. What's his name? Greg. He and Greg both do engineering like work. But Greg is busy. He has a lot of students, a lot of projects. And so it's been kind of hard to connect with him and try to figure something out with him. But Darren wants to get a PhD student on that. And so I sent an email and said, hey, would you be interested in talking to me about it?